Hello, this is Danica Dvorak, and I'm going to be doing a tutorial for problem 13.4.1 out of Introduction to Operations Research by Hillier. This is for Engineering 340 or Operations Research at Liberty University. I hope you find this educational. So the prompt for this problem says that we should use the one-dimensional search procedure to interactively solve the following problem, which is to maximize the objective function of f of x equaling x cubed plus 2x minus 2x squared minus 0.25 x to the fourth. We're supposed to use an error tolerance of 0.04 with a lower bound of 0 and an upper bound of 2.4. Now, my first question when I was going through this is, what is the one-dimensional search procedure? Basically, it is a process that one goes through, and it finds a sequence of trial solutions, and those trial solutions lead the user towards an optimal solution. So every time you go through an iteration, the user sees if the slope or the derivative is positive or negative at the trial solution, and that indicates, whether it's positive or negative, that indicates whether improvement lies immediately to the right or left on the graph. So if the derivative is positive, then the improvement lies to the right, and if the derivative is negative, then the improvement lies to the left. So this sequence of iterations is continued until the distance between the upper and lower bounds is so small that the next trial solution is within that error tolerance that is previously given to the user. That definition is accurate and mathematical, but it's a little hard to wrap your mind around unless you actually do it. So I'm going to walk us through this, and hopefully it'll make more sense by the end. But just so that we are all clear, the notation typically used for one-dimensional search procedures is as follows. You can kind of read through that yourself. I don't know how I'd really read that to you, but there's basically a current trial solution that we need to be keeping track of, a lower bound, an upper bound, and then kind of keeping that error tolerance in the back of our minds. So in order to initialize, we have to know a few things. We have to know what the error tolerance is, and it's given to us in the prompt as 0.04. We also need to know what the lower bound is, and that also is given to us in the prompt as 0. We need to know the upper bound, which is given to us in the prompt as 2.4, and then we have to choose what an initial trial solution should be. And typically, you take the given lower bound and the given upper bound, and you find the average. So here, that would be 1.2. So as we go through these iterations, we have to decide when to stop. And this is where that error tolerance kind of comes into play. So the general rule when you're doing one-dimensional search procedure is that if the upper bound minus the lower bound is less than 2 times the given error tolerance, stop. I've kind of written it out in a little bit of a coding language, if that kind of helps your brain gather information better. But in this case, the general gist is that if the upper bound minus the lower bound is less than 0.08, stop. So we got 0.08 by multiplying our error tolerance, which was given to us as 0.04 times 2. So every time we do an iteration, we take the new upper bound or the new lower bound, whichever one's new, we subtract those bounds, and if those bounds, if the subtraction of those bounds is less than 0.08, we stop and we found an accurate answer. So for our very first iteration, we are going to walk through these steps, and we do this for every iteration. We evaluate the derivative at the current trial solution. So the objective function, if you recall, was x cubed plus 2x minus 2x squared minus 0.25x to the fourth. So we're going to take the derivative of that. We're going to evaluate the derivative, and the derivative is negative x cubed plus 3x squared minus 4x plus 2. And I rearranged the derivative so that it was in order descending for the exponents. So don't get confused if you're looking directly back to that first objective function. I kind of have rearranged it. Anywho, so our current trial solution is 1.2, which we got on a previous slide by taking the average of the bounds, and we evaluate that in the derivative. We put it into the derivative, so we would get negative 1.2 cubed plus 3 times 1.2 squared minus 4 times 1.2 plus 2, and you end up getting negative 0.208. Now, because that answer is less than 0, we're going to make a new upper bound. The new upper bound is going to equal the current trial solution of 1.2. So our lower bound still stays the same at 0, but we are making a new upper bound of 1.2. If you'll recall, the last upper bound was 2.4. And then we don't really need to do it at this step because we only have done one iteration, but just for funsies, to see if we should stop, we'll check the stopping rule. And if you'll recall from the previous slide, it's if the upper bound minus the lower bound is less than 0.08, we should stop. So our new upper bound is 1.2. The lower bound is 0, so 1.2 minus 0 is 1.2, and that is greater than 0.08, so we will still continue. So because our stopping rule did not apply in the last iteration, we move on to iteration 2. Here, the trial solution is now 0.6. And we got this by taking the average of the upper and lower bounds, which, as a reminder, the upper bound was 1.2. We changed that in the last iteration, and the lower bound is still 0. And the average of those is 0.6. We still are evaluating the current trial solution of the derivative of the objective function, and the derivative hasn't changed. We don't take the second derivative or anything like that. We're still just taking the first derivative of the objective function, and I've just recopied it onto this slide. And we evaluate the derivative at the current trial solution of 0.6. So we would do negative 0.6 cubed plus 3 times 0.6 squared minus 4 times 0.6 plus 2, and you end up with a solution of about 0.464, which is greater than 0. So in the last iteration, our solution was less than 0, and we changed the upper bound. In this case, because the solution is positive or greater than 0, we're actually going to change the lower bound. So the lower bound is now going to equal our current trial solution of 0.6. So the upper bound is going to be 1.2, and the lower bound is going to be 0.6. And we will check our stopping rule here. 1.2 minus 0.6 is 0.6, which is still greater than 0.08. So we move on to iteration 3. We now move on to iteration 3. We are going to reevaluate our trial solution once again, so it's going to be the average of the upper and lower bounds. Our upper bound is still 1.2, but our lower bound was changed to 0.6. So we take the average of that, and we get a current trial solution of 0.9. The derivative of the objective function is still the same, and we're going to evaluate that derivative at our current trial solution of 0.9. So this time I actually put in those 0.9 into the function so you could kind of see instead of me just reading it to you. and we end up with a solution of 0.101. Once again, 0.101 is greater than 0, similar to our last iteration. So we're going to change the lower bound again, and it is going to equal the current trial solution of 0.9. So now our upper solution, or our upper bound, our upper bound is 1.2 still, but our lower bound is going to be 0.9. We'll do the stopping rule here again. Our upper bound minus our lower bound needs to be less than 0.08 in order for us to stop. Our upper bound of 1.2 minus our lower bound of 0.9 equals 0.3, which is still greater than our stopping solution of 0.08. So we continue on to iteration 4. We have continued on to iteration 4, and the trial solution is now going to be the average of our upper bound and our new lower bound. So the average of 1.2 and 0.9, which equals 1.05. So our current trial solution is 1.05. And just like all the other iterations, we're going to plug that number into the derivative of the objective function. So we evaluate the derivative at 1.05, and we end up getting negative 0.05. And as you can see, this is less than 0. This is similar to our very first iteration. We had a solution that was less than 0, so we changed the upper bound. So similar to that, we're going to change the upper bound here, and the upper bound is now going to equal the current trial solution of 1.05. And since we're getting kind of close, our error is getting close, I'm going to actually show you the stopping rule instead of just saying it verbally. So the stopping rule, once again, is that the upper bound minus the lower bound needs to be less than 0.08. Here, our upper bound is 1.05 minus our lower bound of 0.9 equals 0.15, which is still greater than 0.08, so we continue on to iteration 5. We now come to iteration 5, which will end up being our final iteration. We do the same thing as every other previous iteration. We find the current trial solution, we average the upper and lower bounds, and we get a current trial solution of 0.975. We plug that into the derivative of the objective function, and we find a solution of 0.025. 0.025 is greater than 0, so we change the lower bound to now equal the current trial solution of 0.975. We check our stopping rule. Is the upper bound minus the lower bound less than 0.08? We take 1.05, which is the upper bound, minus the new lower bound of 0.975, and we find that indeed 0.075 is less than 0.08. So at this point, we find the current trial solution, and that is the final solution. So the new trial solution with those new upper and lower bounds is the average of 1.05 and 0.975, which ends up being 1.0125, and that is the final solution. I hope this video was helpful. If you have any questions, please put them in the comments below, and I will try to answer them to the best of my ability. Once again, I hope this was helpful.